let's talk about the invisible engine that powers your entire digital world. It's this incredible piece of technology you use every single second, but probably don't think about all that much. Your computer's operating system.
I mean, it seems so simple, doesn't it? You just click an icon and boom, a program opens. But what's really going on in that split second? Well, we're going to follow the journey of that one single click to pull back the curtain on the powerful, invisible engine that runs your digital life.
Before anything can happen, before a single window pops up or an email gets sent, we have to meet the mastermind in charge of the whole show.
That mastermind is the operating system, or OS. It's really the foundational software that brings your computer to life. Think of it like this. It's the conductor of a digital orchestra. It's the traffic controller for all your data. It's the resource manager for memory and power. And it's the ultimate authority that makes sure all your hardware and software actually work together without crashing.
Okay, let's get into it. You've just double-clicked an icon, let's say your web browser. That one simple action kicks off this incredible chain reaction. The journey from your click to a fully running program, well, it starts right now. So your click is like the first domino to fall. It's immediately caught and understood by something called the shell. Now, the shell is the part of the OS you actually see and interact with. Your desktop, your icons, all that stuff. It's basically the official translator that takes your human-friendly command, your click, and gets it ready for the system's core to understand. But here's the thing. The shell doesn't have the power to run the program all by itself. So instead, it makes what's called a system call. This is kind of like knocking on the boss's door. It's a formal, secure request asking the OS kernel, which is the real heart of the system, to do something important, like accessing the hard drive and loading that program. And this is where the magic really happens. This is the key transformation. Your click, through the shell in that system call, turns a passive program, which is really just a lifeless file of instructions sitting on your disk, into an active process. A process is that program brought to life. It's now actually running and using up the computer's resources.
The second the OS creates this new process, it also creates something called a process control block, or PCB. You can think of this as a digital passport for that process. It holds all of its vital information, a unique ID, whether it's currently running or waiting for something, how much memory it's allowed to use, everything. It's how the OS keeps tabs on all the different things running at once. Now, that new browser process you just launched, it's not alone. Not even close. In fact, it's just joined a very, very crowded party. Your computer is probably already running dozens, maybe even hundreds of other processes in the background, and somehow the OS has to juggle every single one of them. This incredible juggling act is what we call multitasking. The truth is, your computer's main brain, the CPU, can really only do one single thing at any given microsecond. But the OS is so good at switching between all those processes, we're talking hundreds or thousands of times a second, that it creates this powerful illusion that everything is running at the exact same time. It's a brilliant trick. So, to manage this controlled chaos, all the processes that are ready to go have to wait in line. It's literally like a digital queue at a grocery store checkout. This is called the ready queue. They're all loaded up in memory, just waiting patiently for their turn to use the CPU.
So who gets to decide which process gets to cut in line or go next? Well, that's the job of the CPU scheduler. This is the traffic cop of the operating system. It's constantly looking at that ready queue and, using some very smart logic, it picks the next process to get a little slice of CPU time.
And the scheduler is incredibly smart about this. It knows that some tasks are CPU-bound, like a video game that needs constant calculation power. But other tasks, like downloading a file, are I/O-bound. They spend most of their time just waiting for the network. The scheduler is smart enough to juggle these different needs, prioritizing quick little tasks so your mouse never feels laggy, even while a massive download is happening in the background. Okay, so our new process is in the queue, it's getting its time on the CPU, but where's it actually living? Every single running process needs its own little workspace in the computer's memory, also known as RAM, to store its data and instructions. Now, here is a really mind-bending idea. From its own perspective, every process believes it has all of the computer's memory to itself. This private, personal view is called a logical address. So your browser might think its data is at, say, address 100, but in reality, the OS might have stuck that data anywhere in the computer's actual physical RAM. This constant translation from the process's private view to physical reality is handled by a special piece of hardware called the Memory Management Unit, or MMU. Every single time a process tries to access memory, the MMU jumps in and on the fly translates that logical address into the real physical address in RAM.
And this, of course, leads to a huge problem that every modern computer has to solve. You only have a certain amount of physical RAM, but you want to run a bunch of programs that altogether need way more memory than you actually have installed. So what do?
The solution is one of the most brilliant tricks in all of computer science. It's called virtual memory. The OS cleverly carves out a piece of your much bigger hard drive and treats it like an emergency extension of RAM. When your actual RAM gets full, the OS intelligently moves the least used chunks of data over to the disk, which frees up precious space for the tasks you're working on right now. It creates this amazing illusion that you have a nearly bottomless pit of memory.
So our process has its memory, it has CPU time, but it's still not done. It needs to do things like write to a file, or send a job to the printer, or access the network. And the thing is, it has to share all those resources with every other process running on the system.
And all of this sharing creates a really dangerous situation, a digital standoff. Just imagine this. Process A has control of the printer, but it's waiting for a file that's being used by Process B. At the exact same time, Process B has the file, but it's waiting for the printer. See the problem? Neither one can move forward. They're stuck in a permanent gridlock, and your whole system just freezes.
This digital gridlock has a name. It's called a deadlock, and it is a very serious problem. The good news, though, is that a deadlock can only happen if these 4 very specific conditions all happen at the exact same time. It's like a recipe for disaster. The OS's main job, then, is to make sure that at least one of these ingredients is always missing from the recipe.
And to do that, the OS uses really clever strategies, like something called the banker's algorithm. It basically acts like a very cautious banker. Before it hands out a resource to a process, it runs a quick check. If I approve this loan right now, is there still a guaranteed way for everyone to eventually finish their work? If the answer is yes, the system is in a safe state and the resource is granted. If not, the process has to wait. It prevents gridlock before it can ever start.
So let's just take a step back. From one single, simple click, we've seen the OS interpret our command, create a process from scratch, schedule its time on the CPU, give it a virtual home in memory, and then safely manage how it shares resources with everything else. It is an absolute symphony of incredibly complex operations happening every millisecond. It really is the unsung hero of all of modern computing. It's that invisible engine working tirelessly and silently behind the scenes, managing everything so perfectly that most of the time you don't even realize it's there. It is, quite literally, what makes everything you do on a computer possible. And that leaves us with a really important final thought. In a world that's exploding with connected smart devices, self-driving cars, and incredibly powerful AI, the demands we're putting on our operating systems are going through the roof. They need to be more secure, more efficient, and way more intelligent. So the big question is, what's the next great challenge for this invisible engine as it gets ready to manage a world that is so much more complex than just one single computer?